Hello, I'm Youngwon Choi from Seoul National University in South Korea. I am PhD candidate and Professor Chang-Guk Park is my supervisor. Today, I brief you on my research, auxiliary filter-free incompressible particle flow filtering using direct estimation of the log density gradient with target tracking examples. Here is the outline of my presentation for today. First, I will explain the motivation of this study. Second, I'll describe the background theory for understanding the proposed structure. Then, I'll explain in more detail the proposed method. And then, I'll present two target tracking examples. Next, I'll summarize the presentation. In 2008, Fred Dam and Jim Huang presented a new perspective framework called particle flow for nonlinear filters with log homotopy. This is a kind of a weightless particle filter that performs a Bayesian update by constructing a homotopy function that changes from a prior density to a posterior density. According to the Bayes law, the posterior density pxk given zk is defined as this. From this equation, we can obtain a log homotopy function of lambda like this. When the lambda is 0, the function is equal to the log prior density, and when the lambda becomes 1, the function changes to the log posterior density. Since the homotopy function defines the change in a probability distribution, the Fokker-Planck equation can be used to obtain the imaginary time flow of random variables corresponding to the change in the distribution. Following the flow given by Ito stochastic differential equation, each particle can move itself to perform measurement updates. Since the flow is a virtual process connecting prior density and posterior density, there are various solutions depending on assumptions or constraints. We deal with the incompressible flow that was presented earlier. This flow assumes zero diffusion and zero divergence, and the assumption makes it very easy to solve Fokker-Planck equation. It has the advantage of being easy to derive, simple and fast to implement, and requires no assumptions about distribution. The only thing we need to know to implement this flow is the log density gradient. Fred Dam considered 17 methods to approximate the log density gradient for implementing incompressible particle flow filter, and as a result, the best method is known as the finite difference method using the k-nearest neighbors algorithm. For the finite difference, it is necessary to know the value of the prior density in each of the samples. However, the prior density is given as a set of particles, so the practical implementation requires auxiliary filters such as EKF or UKF to acquire density values. The performance of this structure depends on the performance of the auxiliary filters. Through this study, we intend to eliminate the dependency on the additional filter and to get the divergence from a distribution that is more similar to true distribution than the Gaussian distribution assumed by EKF or UKF. Also, we want to consider more samples, not just k-neighbor samples. Our first approach was to use kernel density estimation. KDE kernel density estimation approximates a PDF by overlapping a specific kernel on each sample. We tried to find the divergence analytically from the approximate distribution through KDE. However, this two-step approach generally has poor performance, and KDE itself is known to perform poorly, especially for high-dimensional problems. While looking for alternatives, we were able to find the least scarce log density gradient method proposed by Hiroaki Sasaki et al. In 2014. They originally proposed this method to cluster samples. The figure on the right is the result of their research. It can be seen that the LSLDG shows better gradient estimation result than the two-step approach using KDE. What we want to show today is how to apply LSLDG when implementing an incompressible particle flow filter and performance comparisons with the existing methods through single target tracking and multiple targeting tracking examples. Here are some backgrounds we need to explain what we've done. First, let's briefly derive the incompressible particle flow filtering PFF. As mentioned earlier, the log homotopy function for Bayesian update is as follows. Here, due to the assumption of incompressible flow, the normalization term does not change with lambda, so the term can be neglected. By understanding lambda as a concept of time, we can assume that random variables x varying with lambda follow the stochastic differential equation. Considering zero diffusion process, the flow can be reformulated as this. The Fokker-Planck equation, which describes the time evolution of the density following the Ito equation, can be summarized by substituting the zero diffusion assumption and the log homotopy function as follows. Because of the flow is incompressible, the divergence of the flow is zero. The minimum norm solution for this equation is like this. From this solution, we can see why we have to find the gradient of log density. Finally, we move each sample by integrating the flow from lambda 0 to lambda 1, and then we can obtain a sample set following the posterior distribution. Next, I'll summarize the least squares log density gradient method. As the name suggests, LSLDG takes the loss function as the square of the error as follows. Here dj hat means the estimated log density gradient, and dj means the true value. By omitting the square term of the true value and substituting dj as the log gradient of density p, we can rewrite it as the following loss function. To approximate the loss from the samples, the Monte Carlo integration method can be used as follows. The estimate of the log density gradient can be modeled as a combination of basis functions and their weights, like this. And each derivative can be represented as a combination of the derivative of the basis functions and the weights. Substituting the model to the loss and adding the L2 regularizer, the loss can be rewritten as this. The least square weight vector for the loss function is given as this, and finally, we get the log density gradient like this. In this slide, I'll discuss about the corner that take into account the properties of the incompressible PFF. The corner presented by Sasaki, who proposed LSLDG, can be described as a decaying Gaussian corner as follows. It consists of a log density gradient term of a Gaussian PDF and an exponentially decaying term. It has the effect of performing KDE using a Gaussian corner, but the effect is reduced as it moves away from the specific sample. The figure on the right is the result of performing LSLDG, to which this corner is applied using samples extracted from Gaussian mixture with two modes. Here, blue dots represent the samples, black line represents the true value, and red line represents the estimated model. As you can see, it shows good performance near the samples. However, far from the samples, the gradient value converges to zero by the decaying term, and for incompressible PFF, when the gradient value becomes zero, singularity problems may occur. Therefore, we propose one option to relieve worries about this singularity problem. The method is to add a unimodal Gaussian corner with the mean and variance of the samples at the sample mean point. The results for this method are shown in the lower right figure. It can be seen that thanks to the added unimodal Gaussian corner, it is possible to prevent the gradient from becoming zero even if it is away from the samples. It was also confirmed that the estimated performance may be slightly lower. The proposed algorithm summarized as follows. First, the initialization phase performs random sampling according to the model of the initial stage. Secondly, the prediction phase propagates particles according to system dynamic model, just like a typical particle filter. Next, the correction phase starts with constructing a set of basis functions according to for the particles distributed by prior density, and then calculate the weight vector for LSLDG according to this. By using this weight vector and the kernel located at the samples of the prior density, the gradient value of the prior density at the moved sample position can be obtained. Calculate the flow by substituting the estimated gradient into the incompressible flow solution, and propagate the particles by recursive numerical integration of the calculated flow from lambda 0 to lambda 1. In order to verify the performance of the presented structure, we performed both single and multiple target tracking simulations. First, I'll describe a single target tracking example using range and bearing measurement. The state variables are two-dimensional position and two-dimensional velocity. The measurements are the range and bearing angle from the origin. Random trajectories are generated according to this dynamic model and this measurement model. The region of interest is set to a 60 by 60 square with the origin as the center, and 100 trajectories only within the region are chosen for results. 5 measurement sets for each trajectory are generated, producing a total of 500 ensembles. For comparison, we implement EKF, UKF, and sequential impotence resampling as a conventional particle filter. Also, we implement the incompressible particle flow filters denoted as IDH-KNN that obtain log gradients using the finite difference method in collaboration with the conventional KNN method. We also implement the incompressible PFF denoted as IDH-FA-KNN using the fast approximate KNN method proposed by Fred Daum et al. To reduce computation. These PFFs use EKF or UKF as an auxiliary filter. SIR uses 300 particles and PFFs uses 30 particles. This is the box plot result for the time average of the horizontal position error of each ensemble. The left one is in full scale, and the right one is scaled from axis 0 to 4 to show the results for the filters in yellow boxes. SIR seems to be the best in terms of position error, but the result of SIR excluded 37 trials that could not be calculated due to the particle collapse. Therefore, I will mention the result excluding the result of SIR. The performance of IDH-KNN with UKF and the presented incompressible particle flow filter with LSLDG, denoted as IDH-LSLDG, seems to be good. The IDH-KNN-UKF has a slightly smaller median than the IDH-LSLDG, but there are 39 outliers for IDH-KNN-UKF, more than the 13 for IDH-LSLDG. The maximum value of the outlier is also smaller in IDH-LSLDG. This is the box plot result for the time average of the horizontal velocity error. Among the velocity error results, the proposed method shows the best performance, and the maximum value of the outlier is clearly smaller than that of other filters. Although IDH-KNN-UKF and IDH-FA-KNN-UKF perform relatively well, the results of these filters have many outliers that are widely distributed. The result of SOAR UKF implies that the outliers of the PFFs with UKF are originated by the malfunction of the auxiliary filter. EKF is the worst performer, and IDH using it as an auxiliary filter is also poor. As a result, IDH-LSLDG has good estimation performance and works robustly for various situations. Referring to the Lee and Quartes simulation, we simulated a system tracking 3 targets using an array of acoustic sensors. The state variables of the ith target are 2-dimensional position and 2-dimensional velocity. Since there are 3 targets, the state space is 12-dimensional. The dynamic model of each target is the same as that of single target tracking examples. The trajectory is constrained to within the 40 by 40 rectangular region of interest. 25 acoustic sensors are placed in the region of interest at intervals of 10. The measurement of the jth sensor is modeled as this. 5 measurement sets are randomly generated for every 100 random trajectories. For comparison, the same 8 filters implemented in a single target tracking examples are tested. SIR uses 100,000 particles, and PFFs use only 100 particles. This is the box plot of the time averaged OMAD. The optimal mass transfer OMAD metric is used to represent the result of multiple targets. The distance metric for the OMAD is Euclidean distance, and the OMAD parameter P is set to 1. The results seem to indicate that the performance of the SIR is the best, but the results do not include the failed 145 trials of the SIR. Excluding the result of SIR, The results for inliers appear to be good in the order of EKF, IDH, KN, and UKF, and IDH, LSLDG. However, more than 20% of EKF trials are outliers, and about 10% of IDH, KN, and UKF are outliers, while the outliers of IDH and LSLDG are less than 5% of all trials. The maximum value of the averaged OMAD is 531 for EKF, 111 for IDH, KN, and UKF, and just 11 for IDH and LSLDG. To compare the velocity estimation result, this figure shows the target averaged velocity error between the true target and the corresponding estimated target with respect to the optimal transportation of the OMAP. The aspect of the velocity estimation result is similar to the position result. You can see that the outlier distribution of IDH LSLDG is more stable than the position result. To sum up, the proposed filter structure shows a relatively good estimation performance for all trials and stable performance in various situations. In this study, we applied the LSLDG to estimate the log prior density gradient for an incompressible particle flow filtering. To verify the performance of the presented structure, we performed a single target tracking simulation and a multi-target tracking simulation. Simulation results showed that the presented scheme works more robustly for various situations than other filters, including the incompressible particle flow filtering structure assisted by UKF and KNN. That's all for now. Thank you for your attention. Any comments or questions are very welcome. Please email me.